name is Bijan. I'm a MD PhD student here at Duke in the Department of Mechanical Engineering and Material Science. And today I'm going to go over a quick intro into data analysis. So throughout grad school, we are taught to run all these experiments and generate all this data, but we're often left wondering, what do we do next? How do we analyze this data and use statistics to make heads and tails of the data and make meaningful conclusions? This can be really confusing since there's so many different statistical tests that we can do, but I made this little flow chart going over some of the basics, statistical tests, and how we can decide which one. But before we get started in diving into this big chart, I thought it'd be helpful to go over some terminology. So data is often categorized as either a categorical variable or a continuous variable. And by a categorical variable, I mean one that has a finite number of values or groups. So as a mechanical engineer, I often do material science testing on 3D printed samples. So in my world, an example of a categorical example of an independent variable is one that is what material I use in my printed sample. A categorical example of a dependent variable could be whether or not my sample fractures after a certain number of cycles. On the other hand, we have continuous variables. These variables have an infinite number of values or groups. So another practical example, in my world, an independent variable could be what percent infill I use in the printed sample. This can range from 0 to 100 and be an infinite value of numbers in between. An example of a continuous dependent or outcome variable would be the strength of the object, whether it be tensile strength or compressive strength. Another couple of terms that are really important to keep in mind when talking about stats is the difference between a null and alternative hypothesis. A null hypothesis kind of our assumption that there is no difference between the group. And that is something you need to assume when you start the test, and you're going to try to reject or accept the null hypothesis. And your alternative hypothesis is that there is some sort of difference between that group. And whether that difference is better or worse, that is for you to determine based on the specific nature of your test. So I always think that everything is a lot easier when we have a concrete example. So pun intended, we have a compressive sample of a concrete cylinder, and we're interested in learning whether material A is stronger than material B. So we're going to put our little concrete sample in a mechanical testing frame, and we're going to crush our sample until it breaks, and then we're going to do that 10 times and measure our compressive strength. So I tabulated all the data on this table, and you can see we have lots of values. So looking at it, kind of looks like material A is stronger than material B, but there are some runs where material B had a higher value than material A. So how do we know for sure, or in a statistically significant or meaningful way, how do we determine which one is stronger? So the first test is always to graph your data. So I made a bar graph of material A and material B and plotted the average or mean, compressive strength, and the standard error using those error bars that you see. And over here, yeah, it still looks like that, that now you see there's some variability in the test represented in the graph, and it still looks like material A is stronger than material B. But we can be sure of that, and if we want to report it, it's important to have some statistics. So what statistic do we use? So let's kind of follow through this table and decide. So our dependent variable or our outcome variable is the compressive strength. So this is continuous because it can range from 0 to infinite or potentially infinite. Everything has an upper ceiling, and it can be any value in between. And then we're going to look at our independent variable. So our what our inputs are. So that is material A versus material B. There are two options. So that's a finite number. So we call that categorical, which means we're going to follow the line and we're going to do an ANOVA or a t-test. And since there are only two examples, we can do a t-test. If there were multiple variables that we were comparing, we'd have to do an ANOVA first and then some more specific statistical tests afterwards. But let's just follow this for this example and perform a t-test. So there are lots of different ways you can run a t-test, either by hand, I wouldn't really recommend that, or using a wide range of statistical softwares. I like to use R Studios. R is free open source platform, and it's really easy to run a wide range of tests using this software. So I'm going to run through the quick example in R. So here's a screenshot of my R script, and we can, and I'll walk through each line of code with you. So first we have to import our data, which is what you see here. And then I'm going to rename our data into a different variable that's smaller and easier to type. So I just called our dataset data. And then I'm going to run the command t.test, and I'm going to call our dataset, which is data, and I'm going to do the $sign and choose strength. So as strength is our outcome variable. And then I'm going to do this little squiggly line, and then I'm going to input our independent variable, or input variable. So that is our material. So I do data $sign material. So here is the results from running the lines of code I showed you earlier. And this is the Welch two-sample t-test. So I'll go through all the important parts of this output and kind of tell you what it means and how to interpret it. So the first thing I highlighted is the p-value. So for this experiment, our p-value is 0.00097. So what does the p-value mean? You hear scientists talk about it all the time. They're always saying, oh, my p-value was less than 0.05. A p-value is the probability that you incorrectly rejected your null hypothesis. So what does that mean? It means it's a probability that you said there was a difference in your groups when no difference existed in real life. So the lower that number, the more sure you can be that there is a true difference between your groups. And it's really important that before you start your experiment, that you decide what is the p-value what's that p-value cutoff? What's the p-value that I need to get below to say or claim that there is a difference? A lot of scientists will use 0.05. And if you go higher than that, let's say 0.1, you are more likely to get a result or say that your results show that there is a difference. But you run the risk of that that is incorrect, that there was no difference in real life, but you're claiming there is in your report. On the other hand, if you lower your p-value cutoff, let's say 0.01, you are more sure when you're reporting that there is a true difference between those two groups, which sounds great. However, you might miss true differences when looking at your data. So in other words, there actually might be a true difference, but because of the natural variability of your data, you're going to assert that no difference exists, and you will fail to reject your null hypothesis more often. So we also have, it gives us the 95% confidence interval. And that's saying that if we took the difference between the two means, that true value, right, because we just have a sample, but the true value between material A and material B, the true difference is, we're 95% sure it's between 7.2 and 23.5. And since that confidence interval is all greater than 0, 0 is not in that confidence interval, we are pretty sure or confident that there is a true difference between that group. Had 0 been in that confidence interval, let's say the confidence interval was -1 to 10, 0 is in that range, in that case, our p-value would be greater, and we would not be able to reject our null hypothesis with our p-value limit set at 0.05. And this test will also output our estimate means, which are the same values we saw in our data sheet before, which is just a good way to check that you imported the correct data and you are running R and coding it correctly. So that is the end of this brief introduction in data analysis. I just want to emphasize that we really only did scratch the surface. There are lots of different tests and nuances to these tests that people get advanced degrees in to study further. Future videos can go over that flowchart further and give more examples of how to go about navigating it and which test to pick, and go further into more advanced statistical tests. I hope you learned something and found this helpful. I look forward to seeing you in future videos.